Hello, good evening. Am I audible?
Yes, ma'am.
Yeah, thank you. Uh, so I hope somebody else join after some time.
Yes, ma'am.
But let me start the session. Anyway, I'm recording the session.
Okay, ma'am.
Uh, so so today's yeah.
Ma'am, before you tell us anything,
Hmm.
I have a few questions. May I ask?
Yeah, please.
Ma'am, as regards this transmission lines and EM waves course, because this is like after a gap of 20 years after my graduation, I am learning this. I
Okay.
learned it in my graduation years, electromagnetic wave theory, and
Hmm.
after that, I haven't. So I'm
Yes.
finding it a little, what should I say, a
Hmm.
very high level course. Is there any
Hmm.
recommendation of any topics that I should cover before I keep on juggling with this? Because I'm finding it a bit difficult, ma'am.
Okay. So
Yes, ma'am.
I will tell you the reason you find it difficult. Because as per the course instructor, uh, there are no prerequisites for this course.
Okay, ma'am.
First thing is you need to know only the basics of like electromagnetics, which is known to any physics student. I mean, any student who had done plus two physics. So,
Okay.
and it's starting from transmission lines. But the point of view from of this course is um towards what you call programming aspect and visualize what we learned in the very basic electromagnetic theory. Even I have learned electromagnetic theory from a very
Okay,
theoretical
ma'am.
perspective. So in this course, they are giving a opportunity to visualize what we learned with a programming aspect, programming content added. So so that is what. So this course has two aspects. One is the practical thing of aspects of electromagnetics. Second is you use a programming to visualize what you learned in electromagnetics. It is really hard to understand electromagnetics, so that is some perspective
Yes, ma'am.
towards the programming. So there is so if you look at the lectures, there is a uh, octave uh, octave coding you might have
Yes.
seen. So
Yes, ma'am.
octave is a freely available. You can download it and just try I mean, you can just copy the code, the whole
Okay.
code from the lectures, and you can try how that code works. Even if you don't understand what each line means, you can try out the
Okay, ma'am.
same code. So you will be at the end of the day you will be able to visualize what you learn in electromagnetics. That is the perspective. That is my suggestion. There is no prerequisites for this course, or just basics of electromagnetics.
Okay,
That's all. And this course starts with
okay, ma'am.
transmission lines. So as we have come across, so I'll start with my today's session. Uh,
Yes.
okay, so week one we have come across transmission lines, especially the lossless and lossy transmission lines in the week two, and followed by week 3, wherein we came across some concepts of Smith chart, impedance matching. So, so far I have covered 3 sessions, 3 tutorial sessions, which is available in NPTEL site. So, this is my fourth session. So, the first 3 sessions is covering the content of week 1, 2, 3, 4. So if you have any, if you would like to go through any of the sample problems from the week 1 to week 4, you can see the previous sessions. So today's session, we have the week 5 content added. So along with week 5 content, I think the assignment 5, which is due on the coming Wednesday. So we'll just go through some of the week 5 content and some sample questions. And also, I will try to incorporate a few questions, assignment questions, or a similar questions. I can say similar questions as that of assignment questions, so that you can clarify your doubts wherever it happened in the previous weeks. So today I'll start with week 5 content, wherein you come across the transmission lines is being concluded first of all. So to discuss about that, first thing is we need to understand what is the limitation of a transmission line. So I hope you might have gone through the lectures and you have understood the fact that depending upon the frequency, basically the alpha, the attenuation constant. So if the frequencies are lower, alpha is low. That is attenuation constant, or that means the attenuation of the wave along the transmission line as it propagates along the transmission line. But if you go for higher and higher frequencies, sorry, I have to just plug in my laptop to the charger. Okay. So for higher and higher frequencies, you have a higher attenuation constant. That means at higher frequencies, as the wave propagate along the transmission line, it is going to attenuate more. So that is one limitation with the transmission line. Now, how do you overcome that limitation? You need to have something called as repeat amplifiers. That means if the signal is getting weakened, you need to amplify, repeatedly amplify that at several points. Okay. So as we go for higher and higher frequencies, the need for this repeat amplifiers becomes closer on the transmission line. So this is one of the limitations with the transmission line. So uh, then we come across, so as we are moving towards plane waves, the free space transmission, and towards the other ways of transmission, first we look at Maxwell equations. So these are very famous equations, especially if you have learned the very basic electromagnetic theory. You have come across this four equations. Let me write it down here. Del dot B equal to 0, del dot D equal to rho, del cross E is equal to minus dou B by dou T, and del cross H is equal to J plus dou D by dou T. So, although these equations are called as Maxwell equations, basically this is a compilation of equations given by several scientists. Say this curl equation, del cross E, this was given by Faraday. So this is basic Faraday's law. So if you have learned the very basics of Faraday's law in your physics in your 12th standard, so that same Faraday's law has been written in this form: del cross E is equal to minus dou B by dou T. That is, changing magnetic field causes a change in electric field. So this is a coupled equation. If you see what is B, magnetic field, B can be written as mu into H. So in the same equation, you have electric field and magnetic field. So we call it as a coupled equation. So if you see the second curl equation, del cross H is equal to J plus dou D by dou T. This D is epsilon into E. Again, E and H are coupled. So these equations were already given by several scientists. Say the second equation, del dot D is equal to rho, had been given by Gauss law. Okay. So, and both of these are being given by Gauss law. And this equation, del cross H is equal to J, this was the contribution from Maxwell. Maxwell added this second term, that is, previously it was del cross H is equal to J alone, but this dou D by dou T component had been added by this Ampere. So basically the Ampere's law had been modified by, so del cross H is equal to J was the Ampere's law. So that had been modified by the Maxwell. So you got the modified Ampere's law, which is, so all these four set of equations are called as the Maxwell equations because it was formulated finally altogether. Now, what is the analogy of this with a transmission line? So, you have come across transmission line before. So, if you remember, during the discussions of transmission line, we came across voltage and current. Whereas, when we come to the free space equations, we take these two terms, that is electric field and magnetic field. So, these set of things are basically analogous. So how is that analogous? If you look at the equations, you can see that here electric and magnetic field is varying with respect to time, whereas in transmission line equations you have seen that the voltage and current were varying with respect to time. And if you can come to this wave equation, if you have gone to the lectures of this wave equation, you have seen this del square E is equal to mu epsilon dou square E by dou T square. Okay. What is the speciality of this wave equation? To give a brief of that. So how do we get this wave equation? We try to decouple. So as I told before, E and H are present in the same equation in both the curl equations. So this is curl equation 1 and this is curl equation 2. In both of this, E and H gets coupled. So to decouple that, I mean we need an equation in E alone. So that is what, by decoupling, we got this wave equation. So now this has only E. This has only E. Okay. So this has very important, this is a very important relationship. This gives a very better understanding of the electromagnetic waves. Now let us have look at some questions to see whether we have understood about what we understood about the Maxwell equations. And okay, let me start with this question. I'll just read it out. What was Maxwell's contribution to the equations named after him? Select one or more. If you can see the screen, please type in your answers in the chat. What do you think is correct among these options? So I can read it out. He just compiled them all into a single framework. The hard work and exact equations were already derived by Gauss, Ampere, and Faraday. Second thing, he added a displacement field term that was missing in Faraday's law. Third option, his correction gave a consistent particle theory of light in joint work with Einstein. And fourth option, he replaced the electric field by displacement field to give a more correct version of Gauss law. He added a displacement field term that was missing in Ampere's law. His correction gave a consistent wave theory of light. Which among these do you think are right? There might be one or more answers. So, whatever you think is exactly correct. Yes. So, as Sapna, you have answered, yes, it is correct. E is the right option. I will tell you why A is not the could not be told as the right option. So this E is one right option. He added a displacement field term that was missing in Ampere's law. So as I discussed before, Ampere's law was only del cross H is equal to J. So if you add dou D by dou T to that, so this addition had been made by uh, Maxwell. So this was his contribution. Now we can't say that he just compiled them into a all into a
Ma'am, I
single.
understood this. May I answer?
Yeah, yeah, please.
Because he didn't only compile, he
Mm.
added an element. That is why A is not an option.
Yeah, yeah, true, true, true. That is what I wanted to convey.
Thank you.
And another thing is, so maybe in my discussion I didn't exclusively say this. There is one more right option, that is, his correction gave a consistent wave theory of light. Okay, so if you go to the wave theory, you come across this, the why this has made consistent. You can learn that in the coming lectures more. So this is also a another option to this question. Okay, so let me move to another question. So two sources exist in a given region. Say we have a source Q1, let me call this as Q1, another source is Q2. The first one produces an electric field in space which is found to be curl free. Okay, so now let me make that into a graphical representation. So first source will produce an electric field, okay, in space, and it is found to be curl free. What do you mean by curl free? What is curl? We call del cross as curl. So del cross E is 0. So that is the meaning of this sentence. Now coming to the second source, produces a magnetic field. Okay, let me write magnetic field as H, or maybe I can write it as B also, because B is equal to mu H, and which is steady. Okay, what do you mean by magnetic field is steady? So if I say it is steady, that means it is not varying with respect to time or space. It is already given in the question. Okay. If it is not varying with respect to time or space, I can say dou h by dou t or dou h by dou z. Okay. Z is the space term. So these both will be 0. Now suppose if I switch off the second source. Okay. This has been turned off. Okay, there is no source, and we wait for the transient effects to die out. Transient effects means the immediate effects, that's all. And will there be any change in electric field in the region? So the question is about the electric field. If this Q2 source is switched off, will there be any change in the electric field? Our first source is being unchanged. So please go through the options and answer what you feel. You can give your answer in the chat. Okay, let me go through the options once. No, because the time rate of change of magnetic field is zero in steady state. So no electric field can be generated. Okay, so here it says that magnetic field is zero. Okay, in steady state. So no electric field can be generated. So if magnetic field is zero in steady state, there cannot be any electric field. Okay, so coming to second option, electric and magnetic fields are always coupled. Okay, it is coupled. So the statement partially it is correct. Okay, electric and magnetic fields are always coupled. But is that the case here? That we need to understand. Okay, because of that whether it changes or not. Coming to the third option, Ampere's law says that there is an electric field due to the magnetic field. Okay. And the fourth option is no, because in this case, electric and magnetic fields are uncoupled. Okay. Now let's see what is happening. Let me write the curl equation first. So what is the curl equation? Del cross E is equal to minus dou B by dou T. Now we say that B, that is magnetic field, is steady. It does not vary with respect to time. So what is dou B by dou T will be 0. Okay. So now what is the meaning? Del cross E is 0. That is, there you can have an electric field for which the curl will be 0. Okay, curl will be 0. That means electric field can exist even when the curl of that is 0. Okay, so here now what is happening, because this is not varying with respect to time, because the magnetic field is steady, del cross E is 0. Okay, and these are not coupled. E and H are not coupled. This is a special case. So even if the source Q2 is off, there will still be existing the same electric field. Okay, so I hope this is clear. So, but if in general case, always remember electric and magnetic fields are coupled. Now coming to some questions from transmission lines. These are some selected questions based on the assignment questions. So consider the transmission line setup shown in the above figure. Find the input impedance looking into line 1. So we need to find the input impedance looking into this line. Okay. Now here we can see that this line, that means from here to here, this is line 1. This has a characteristic impedance Z0. From here to here, this is line 2. So when I say line 2, this is both. Okay, and this again has a characteristic impedance Z0. Now look at this one. This is line 3. Again, this also has a characteristic impedance Z0. Okay. Now, how do we solve this question? Finally, we need this input impedance. So let us solve it part by part. So first let us solve what is this one and what is this one. Okay, so what is this input impedance? So what do we have here? This is a lambda by 4 line. What do we call lambda by 4 line? As quarter wave transformer. So this quarter wave transformer has a load connected, that is 200 ohms, and the characteristic impedance of the quarter wave transmission line is Z0. See, the basic equation of quarter wave transformer I will tell you. If this is Z0 and if this is ZL, what is Zin in case of a quarter wave transformer? Zin is equal to Z0 square by ZL. Okay. So this is the case with any quarter wave transformer. Okay. Now, in that case, can you tell what will be? Maybe I can write this as Z in 1. What is Z in 1? Can you tell what is Z in 1? Z in 1 will be Z0 square divided by 200. Okay. Now, similar way, let's look at Z in 2. Okay. What is Z in 2? How do we say Z in 2? Z in 2 is Z0 square divided by, what is ZL here? This is a short circuit. So, may I know what is ZL? If it is a short circuit, what is ZL? ZL is 0. Okay. So, yes, as Sapna said. So, Z0 square divided by 0, Z in 2 will be infinity. Now, look at this, how this line is being connected. So, it is like Z in 1 is coming in parallel with Z in 2. Okay. So, what will be the resultant? Z in 1 is coming in parallel with Z in 2. Okay. So, Z in 1 parallel to infinity. Okay. Z0 square by 200 parallel with infinity. What you will get? You will get Z0 square by 200. Okay. So, that will be your resultant at this point. Okay. Now, what is Z in again? Again, look at this. This is again a lambda by 4 line. Okay. If it is a lambda by 4 line, use the same equation. Z0 square by, what is the load impedance here? So, load impedance is nothing but this one. So, Z0 square by 200. So, the final answer will be 200 ohms. I hope this is clear. If you have any doubts, please ask.
Ma'am, please explain this one more time.
Okay. So, basically you have this kind of a transmission line. Okay. This is one transmission line. This is the second transmission line. So, if this gives Z in 1 and this gives Z in 2, Z in 1 parallel to Z in 2 will be the impedance here. Okay. Then again Z in. How do you find it? Z in is equal to Z0 square divided by Z in 1 parallel Z in 2. Okay. So this is the basic idea. Now about the quarter wave transformer, I hope it is clear.
Yes, ma'am.
Okay.
Understood.
Okay. Now let's move on to another question. I hope the question is clear on the screen. So you have a load impedance 100 ohm and you have a characteristic resistance 50 ohm. Now, how do we do a matching? Okay, if you have a ZL and Z0, if Z0 is not equal to ZL, we say there is a mismatch. So this can be made equal with the help of a matching network, which can be a LC matching network. That means with the help of an inductor and capacitor. So it could be configured in any way, L in parallel, C in series, or however you want. Now we need to understand how do we want to connect the inductor and the capacitor. So given load is 100 and given characteristic resistance is 50. Okay. Now how do we connect? LC. Okay, that is the question. So we need a we need a proper matching circuit. We need to choose a proper matching circuit among the four. To do that, let me give you some tips. There is a possibility to add a series capacitance or a parallel capacitor. Now, there is also a possibility to add a series inductor or a parallel inductor. Okay. Now, I hope you remember the Smith chart, discussions on Smith chart. So Smith chart, if you remember, it had circles like this, and you had R circles and X circles like this. Okay. And center of this Smith chart was the matched point. And if you remember clearly, the upper half of the Smith chart, we call it as inductive reactance, and the lower half of Smith chart, we call it as capacitive reactance. Now, so the trick here is if you add a series capacitor, okay? So if you add a capacitor, it moves towards lower half of the Smith chart. If you add an inductor, you move towards the upper half of the Smith chart. Now, what about series and parallel? So there is constant R circle and there is constant G circle. So if you remember, R is resistance and G is admittance. G is conductance. So if you move, so if you connect a series element, either inductor or capacitor, you are moving along the constant R circle. Okay. Series means you are moving along the constant R circle. Now, parallel, if you add any component, that means you are moving along the constant G circle. Okay. So, now to the load. Okay. What is our load? 100 ohm. So, in the Smith chart, you mark the point. So, what is the point? The load impedance. So, from the load impedance, you need to move towards the matching point. Okay. Suppose if you add a parallel inductor, first option. So, to the load, you add a parallel inductor. So, what happens will be, so in option A, what happens to the load? You add parallel inductor, then series capacitance. Now what happens? How it moves? Parallel inductor means it moves along the constant G circle towards the upper half of the Smith chart. Okay, so from 100 ohm, it moves along the G equal to 0 circle in the towards the upper half. Now, if you add series capacitance, what will happen? It will move along the constant R circle and finally towards the lower half of the Smith chart. Basically, what will happen? Finally, it will reach the matched point. Okay, say I can just roughly draw this on the Smith chart. Suppose if you add a parallel inductor along the constant G circle, so this move, say this move something like this, and finally it comes. So if you add a series capacitance, it comes back to the matched point. Okay, so this movement is along G circle. Okay, this movement is along G circle and this movement is along R circle. Okay, so that is how, so this is not a proper Smith chart. You can look at the proper Smith chart and understand this much better. So this is the idea. Okay, so in the second case, you see option B, you see parallel capacitance and series inductor. So parallel capacitor and series inductor. So if you connect a parallel capacitor, you move along constant G circle, or I can say G equal to 0 circle, and move towards the lower half, and then you move along the constant R circle towards the upper half. Okay, so this means what? You move downwards first. Okay, from the point you move to, say if you can, so here say if this is the point, you move downwards first and along the G circle and go and intersect the R circle. Then again you move up along the R circle and meets the matched point. Okay, so these are the two options possible options. Okay, so these are A and B, whereas C and D are not a possible choice. So we can move either like this or like this. There are only two possibilities. So from a 100 ohm towards 50 ohm, or I mean towards a matching point, you can move only in two ways. So either with option A or option B. I hope this is clear. Okay. So now let's move to another question. So this is a numerical. So let's, if you have a pen and paper, you can try out please. Use a calculator and try to find the answer. Impedance of a section of 75 ohm lossless transmission line of length zero point 0.4 lambda. Okay, so we have several understanding from this question. Z0 is 75 ohm. It is a lossless transmission line and the length of the transmission line is zero point 0.4 lambda and it is terminated in a short circuit. What do you mean by terminated in short circuit? ZL is 0. So you have a transmission line of length zero point 0.4 lambda. At the load end it is short circuited and the characteristic impedance is 75 ohm and you need to find this impedance. So we have a direct equation for this. Zin is J Z0 tan beta L. So this had been in the discussions. J into 75 into tan beta. How do you calculate beta? 2 pi by lambda into L. L is zero point 0.4 lambda. Okay, lambda gets cancelled. J 75 tan of 2 into zero point 0.4 pi. So basically 0.85. Can you try calculating and find out the answer, please? You can just type in the only the options 1, 2, 3, or 4. Always remember this is in radian. When while doing the calculations, please keep an eye on radian, degree, and all that. Yes, right answer, Sapna. It is minus j 54.5j. Okay, so I hope this is clear. Let's move on
Yes, ma'am.
to next. Characteristic impedance of okay, so this is a question. Okay, so this there is a transmission line. So the question is incomplete little bit. So transmission line of characteristic impedance set not equal to 60 ohm, and I need to add something also. Length is equal to zero point 0.6 lambda. Okay. So we have two details, 60 ohm characteristic impedance and length is 0.6 lambda. And it is terminated in an impedance. So this is your load 120 plus J 240. Enter the values of real part of input impedance of the line. See, you have ZL and Z0 and you also have the L length. Now, first part A and part B can be done if you know this equation Z in, okay, Z in equal to Z0 into ZL plus J Z0 tan beta L divided by Z0 plus J ZL tan beta L. Okay. So if you know this equation, you can calculate the input impedance. So that will be complex. If you take the real part, you will be able to answer the first. And if you take the imaginary part, you will be able to answer the option B. I mean question B. Okay. So we know Z0, ZL, it is just substitution. And we also know length L. And always remember beta is what? 2 pi by lambda. So if I write beta L, it will be 2 pi by lambda into L is zero point 0.6 lambda. Okay. So finally you will get it as 1.2 pi. Okay. So beta L is 1.2 pi. Try substituting and try to find the answer for input impedance. I think it takes some time. For the interest of time, you can try this out. For the interest of time, I'll just give the answers. Real part of Z in. So basically, you will get it as 4.8 minus 92.4j. Please do try. So real part will be 4.8 and imaginary part will be uh, minus 92.4. So let's move on to the C part, real part of reflection coefficient at the load. Again, reflection coefficient, how do we calculate? Very basic equation which we should always remember, ZL minus Z0 by ZL plus Z0. ZL is 120 plus J240 minus Z0 is 60 divided by 120 plus J240 plus 60. Okay, so this comes out to be 60 plus J240 divided by 180 plus J240. Okay, so if you simplify this, you can calculate gamma. So I hope you remember how to calculate the, uh, how to divide two complex numbers. So it's always easy to convert.
Rationalize.
Yeah. It's all. We need to convert this to polar basically, and just so 60 plus J240. You take the polar of this. So say if you get A angle B, you take polar of this one, you get C angle D. So to divide this, what do you do? A by C and angle B minus D. Okay. So this is the easiest way you can try. So you must be getting 0.824 angle 22.83. So this one, if you again, you can convert back to rectangular form. Okay. So this is available in calculator. You can put just rectangular of this and you will get the rectangular answer. So 0.76 plus 0.32j. Even you can do in online calculators. It is possible to do even in online. There are some possible scientific calculators online, which even rectangular polar conversions also you can do. So again, real part of reflection coefficient is 0.76 and imaginary part of reflection coefficient is 0.32. Now, the question E, magnitude of the reflection coefficient. So if you have a real and imaginary part, it's easy to calculate the magnitude. 0.76 square plus point.
A square plus B square kind of.
Yes,
Yes,
that's
ma'am.
it. So if you try that, you must get that. Magnitude is 0.825. Now, how do we do the last part? Voltage standing wave ratio. For this, you need to know the very basic equation of VSWR. It is 1 plus mod gamma divided by 1 minus mod gamma. So mod gamma is the magnitude. So 1 plus 0.825 divided by 1 minus 0.825 is equal to 10.43. So this is the VSWR. So these are all basic equations. The equation for input impedance, equation for reflection coefficient, equation for VSWR. Hope I can move on.
Yes, ma'am. But before that, can we zoom the screen? so that I can
Okay.
see the question part on a
Oh,
bigger screen. My screen is full size, but
oh, okay, okay.
okay, okay.
Just a moment. So you need to see which part? I mean,
No, no, this one is clear. Question number 20 is clear. Whenever we
oh,
are doing the next one,
oh,
just a
okay.
bigger window. Yes, ma'am.
Oh, okay, okay, okay.
Thank you, ma'am.
So, okay, coming to the next question. So this is this was an assignment question. Not exactly the same. This is a similar assignment question from the previous week. So I felt this was a little confusing for few people. So I took this for a discussion. So this this is a waveform of voltage on a lossy transmission line. So when I say lossy transmission line, the wave amplitude is reducing, as you can see. See the amplitude of the wave in each cycle, you see the amplitude is reducing, keep on reducing. Okay, so that is your lossy transmission line. In a lossy transmission line, R and G exist. Okay, R, sorry, in a lossless transmission line, R and G will be 0, due to which alpha will be 0, whereas in lossy line, R and G are not equal to 0, due to which there is an attenuation constant which will make the wave have a decay. Okay, so there is something like an exponential decay of the wave as it propagates along the transmission line. Now, if you look at the wave transmission, you see this is called as Vmax and this is called as V minimum, voltage minimum and maximum. That's all. Now, so this there is one more information. Lambda is 3 mm. That is the wavelength. And this we are saying the spatial dimension in terms of lambdas. 1 lambda, 2 lambda, 5 lambda up to that. And this axis is in voltage. Now let us see the question one by one. First question for so these questions are based on the graph. Okay. First question, voltage wave for the voltage wave of wavelength 3 mm on a lossy transmission line shown in the plot at a particular time instant. What is alpha? Can you calculate the attenuation constant from this figure? That is the first question. So, how do we approach that question? Uh, the easiest way is you see this is V minimum. What is the value of this V minimum? It is something around minus 0.9. Okay, and let me take another V minimum. Say this is V minimum. So if I extend it here, it will be something around zero point 0.5. Okay, so minus zero point 0.9 is reduced to minus zero point 0.5 in how many lambdas? Okay, you see how in how many lambdas that reduction has happened. So this is lambda, this is 5 lambda. So 5 lambda minus lambda, it is in
4 lambda.
4 lambda. Okay, so this has happened in 4 lambda. So how do we write that as an equation? As I told before, the decay, that means the wave has a decay which is exponential decay. Okay, so to write that, minus zero point 0.5 divided by minus zero point 0.9 is equal to e raised to minus alpha z. Now, what is z here? Z is the distance traveled by the wave. Here it is 4 lambda. Okay, so this will be e raised to minus alpha into 4 lambda Again, this is 0.5 by zero point 0.9. Okay. Now let me take, so here you have E and here you, so to make it easier, take a logarithm on either sides. So ln of zero point 0.5 by zero point 0.9, this will ln E becomes minus alpha into 4 lambda. Okay. Now here you know the value of lambda. Now can you calculate alpha? ln 0.5 by zero point 0.9 divided by, there is a negative sign, by 4 into lambda is 3 millimeters, 3 into 10 power minus 3. Is it possible? Can you quickly calculate? Okay. In the interest of time, I think I can just give the answers. It is 48.98 and the unit of alpha will be Napier per meter. So approximately, if we look at the options, it's approximately 50 Napier per meter. Any doubts in this?
No, ma'am.
Okay. So in that case, let's move on to the next part. If the input power of the transmission for the transmission line is 1 watt, what is the relative power available at a distance of 5 lambda on the line? Okay. So this is a question on like in the transmission line, its input power is given, that is P, and after a distance of 5 lambda, what is the output power? That is a question. So let us write P naught by Pi. So since it is powers, let us write 10 log of P naught by Pi, that is 10 log of e raised to. So if you remember here, voltages ratio we have written as e raised to minus alpha z. So because it is power, it is voltage square, it becomes e raised to minus 2 alpha z. Okay, so this is minus 20 alpha z log of e, minus 20 alpha z log e. So minus 20 into alpha, we already know from the previous uh, uh, part, that is 50 Napier per meter, and Z is 5 lambda, so 5 into lambda value you already know, 3 millimeters into log of E. So once you simplify and get the answer, you must be getting minus 6.5 dB. Hope this is clear.
Yes, ma'am.
Okay, so moving on to the third part of this question. With the data shown in the plot, phase velocity on the line can be determined. Is it true or false? So, what is phase velocity of the wave? First thing we need to understand, to find out phase velocity, what do we need? Phase velocity is basically omega by beta. Okay, we know, if we know omega and beta, then you can find out the phase velocity. From the information in this graph, you only have the voltage levels, that is the Vmax, Vmin, and depending upon the spatial positions, and you only have the lambda, that is the wavelength. Okay, you don't have the angular frequency of the wave which is traveling. Okay, so this cannot be determined. So this is a false statement. If frequency was given, it could be found. Now, moving on to another question. Okay, maybe this question is something related. Okay, lossless transmission line of characteristic impedance 50 ohm. So Z0 is 50. Loaded with a short circuit. Okay, so you have a transmission line which is short circuited. Z0 is 50, ZL is 0. Now, this has to be designed, okay, to act as inductive or capacitive. This is very important. You need to design this to make it what? Either an inductive reactance or a capacitive reactance of 150 ohm. Okay, how do we make that? So if it is an inductive reactance, we call it as plus Jx, and if it is a capacitive reactance, we take it as minus Jx. So this is inductive and this is capacitive. So it should be plus or minus J 150. So this is our goal. You need to design a uh, impedance, that is plus or minus J 150, with this particular transmission line. That is, it has a short circuit with a characteristic impedance of 50 ohm. Now, what should be the length of this line so that this becomes plus or minus J 150? What are the, or the question could be, what are the possible lengths of the line? At different lengths, this could be plus or minus J 150. So how do we solve this? We already know part of this because we have already solved Z in. So the equation for Z in is, if it is a short circuited load, Z in is J Z naught tan beta L. Now, if you know this relationship, then this is a straightforward question. So what is Z in? What do you need to create? Plus or minus J 150. So let me write plus or minus J 150 is equal to J into Z naught is 50 tan beta L. Beta is 2 pi by lambda into L is something which we need to find. Okay. Now 50 and 150, J and J gets cancelled. This will become 3. So I can write tan beta L is equal to plus or minus 3. To get tan beta L plus or minus 3, which of the options give us tan beta L plus or minus 3? So L is in terms of lambda. So just remember, length of the line in terms of lambda. That means beta is basically 2 pi by lambda and L is like x lambda. Okay, so beta L will be, what will be beta L? 2 pi by lambda into x lambda. So lambda gets cancelled, so it is 2 pi x. So tan of 2 pi x is equal to plus or minus 3, for which what is x? What are the possible values of x? Let's take point 2. Okay, tan, first option, tan of 2 pi into point 2. What will be that? Tan of 0.4 pi. What is tan of 0.4 pi? So basically it is tan 72. So tan 72 degree is approximately 3. So yes, first option is a right option. Okay. Similarly, if you substitute zero point 0.3, so basically it will become 2 pi into zero point 0.3, zero point 0.6 pi. So zero point 0.6 pi will also give you 3 approximately. So zero point 0.6 into 180 will be 108 degree. So tan 108 is again minus 3. Okay. So this, if it is plus 3, I mean tan zero point 0.3 into 2 pi, that means 0.6 pi will be minus 3. It could be either plus 3 or minus 3. So zero point 0.3 is also an option. Similarly, one more option is out there, that is zero point 0.8. So tan of 2 pi into zero point 0.8. So that will be 1.6 basically. 1.6 1.6 pi is 288. So tan 288 is giving us minus 3 again. Okay. So these are the possible choices. Hope this is clear.
Yes, ma'am.
Okay. Okay. So I have one more question in line. So this one, basically we have a voltage wave at 1 gigahertz. So you know the frequency is traveling on a transmission line in plus x direction. This is a very important information given to us. Any wave transmission in plus x direction, uh, how do we write that? That is something which we need to understand. Uh, if you remember, in the discussions, it was mentioned, say omega t. So the phase of that will be omega t minus beta x. If the wave is traveling in plus x direction. If it was traveling in minus x direction, this would have been omega t plus beta x. Okay. So let us keep that point in mind. Moving on, the primary constants of the line. So primary constants are given. Let us write them down. 0.5 ohm per meter. Inductance is zero point 0.2 microhenry per meter, and G is zero point 0.1 mho per meter, and C is 100 picofarad per meter. Now, the wave has 30-degree phase at time t equal to 0. Okay, so when the wave starts, okay, at time t equal to 0, phase of that wave is 30 degree. Okay, now at a x is equal to 50 centimeter, what is the phase of the wave? And it is not just x is equal to 50 centimeter, and also there is one more parameter when time is equal to 1 microsecond. What is the phase? Okay, so there are two things. First thing, based on the primary constants R, L, G, C, what we can calculate? Uh, from RLGC, you can find out Z and Y. What is Z? R plus j omega L. What is Y? G plus j omega C. Now, if you know Z and Y, what is gamma? Gamma is root of Z into Y. And we also know gamma is nothing but alpha plus j beta, where alpha is the attenuation constant and beta is the phase constant. This is the parameter in which we are interested, beta. Okay. So if you know the beta, that means the phase constant, then you can substitute here in the equation of a wave, omega t minus beta x. So this is the phase. What is the phase? Omega into t. Omega, do we know omega? Yes, we know the frequency. So 2 pi f will be uh, omega. Do we know time t? Yes, we know the time t. It is 1 microsecond. And do we know the beta? Yes, we know the beta if we find out the propagation constant gamma. And what is x? Do we know the x? Yes, we also know x is 50 centimeter. So if we know all these parameters, we will get the phase at this, the phase omega t minus beta x. Okay. And we also know in the beginning, at the start of the wave, at time t equal to 0, phase was say phi naught, 30 degree. Okay. So here what will be the phase? This much phase is being acquired. So this is say phi dash. Okay. The acquired phase is phi. So phi naught plus acquired phase phi will be what? Phi dash. So this is the concept of the problem. Is this concept clear?
Yes, ma'am.
Okay. So now let us solve it one by one. So how do we calculate Z? R plus j omega L. 0.5 plus j omega is 2 pi f. So 2 pi into f is 1 gigahertz. 1 into 10 power 9 into what is L? 0.2 into micro, 10 power minus 6. So we calculate Z. Similarly, do Y. So G plus j omega C, 0.1 plus j into 2 pi into 1 into 10 power 9 into j omega C. C will be 100 picofarad, 100 into 10 power minus 12. Okay. So Z and Y is found. So let me write out Z is 0.5 plus J 1256 and Y is 0.1 plus J 0.628. Okay. Now convert this rectangular to polar. So if you convert, this becomes 1256 angle 90. Convert this y to polar, this becomes 0.64 angle 81. Now, how do we find gamma? Gamma is root of z into y. So, see this. This is z in polar, y in polar. If you take the multiplication, what will happen? Square root of 1256 into 0.64. If you take multiplication means add 90 and 81. Okay. 90 plus 81. So gamma is equal to root of 1256 into 0.64 will give us 803.8 angle will be 90 plus 81, 171. Now, taking the square root, what do we do? Take the square root of the mag.
28.35.
Yeah, 28.35. Take the magnitude square root and divide the angle by 2. 171 by 2. So that will be 85, approximately 85.5. So convert this to rectangular. This is in polar, convert it to rectangular. What do we get?
Yes, ma'am.
2.2 plus 28.26J. Now what is that we are interested in? We are interested in the imaginary part, that is the beta.
28.26. Yes, ma'am.
So we got the phase constant. So once we get the phase constant, beta is 28.26. What is phi? Omega t minus beta x. Omega is 2 pi into f. That is, f is 1 giga into time t is 1 microsecond, 1 into 10 power minus 6 minus beta is 28.26 into x is 50 centimeter. Let me make it in meters, zero point 0.5. Okay. So this calculation, if you do, phi value you will get. Okay. So whatever you get will be in radian. So approximately it will come out to be 6269 radians. Convert it to degree, that becomes 35,900, I mean 359190 degrees. So basically if you take, it is nothing but 997 into 360 plus 0.75 into 360. Okay, if you take how many 360s it is there. So it is 0.75 into 360. Okay, so basically the initial phase phi naught is 30 degree. Okay, so you add that 30 degree to this one. So phi dash will be 30 plus 0.75 into 360. So you will get it as 300 degrees. Any doubts?
No, ma'am.
Okay, so that's all for this today's session. We are, if you have any particular doubts, you can ask, or we'll try to wind up the session.
Ma'am, I want to know how can I contact you? Is it